Thank you for inviting me, and thank you for the people who are tuning in. It's great to know there are real people out there in the world. We're still locked down here, so this is, yeah, it's a double treat for me. So yeah, I'm going to be talking about moonquakes and an introduction to what we know about the moon from Lunar Seismology. And my name is Ceri Nunn, and I'm from Jet Propulsion Laboratory. So if we just start with some field work, I'm not a huge fan of field work myself. And this is Buzz Aldrin installing the equipment that we're still using today, almost 50 years later. If you just look at the what they're kind of chatting about while he's installing it, and I really recommend the website Apollo in Real Time, unless you've actually got a deadline or some real work to do, then I probably wouldn't recommend it. But they're just chatting about what Armstrong can see, he's looking at some hand samples, and Aldrin is complaining that he can't get the thing to level. And I just think it's worth remembering how difficult it was to install this equipment. And what a kind of huge debt we owe to the people who did it. So I'd like to start there. So a quick outline of the talk. We have, so I'm going to be talking about moonquakes. I'm going to start by showing you a lunar seismogram, and then going to show you some moonquakes. Then I'm going to talk to you about what that means about the internal structure of the moon, and then what we could learn from a future lunar mission. So let's begin with the lunar seismogram. So this is a lunar seismogram from Apollo. And the first thing to notice about it, I think, is just the length of it. This is a 1-hour record. So this is, for anybody who works on Earth, this is just crazy. It's, you know, like Earth seismograms are usually over in like maybe a couple of minutes at most. So that's that's what we're dealing with. This is this energy which can last for a whole hour. And this is a pretty kind of typical record. It's a meteoroid impact. It's picked up by Apollo 12's seismometer. And if we just start with some of the things that we can kind of see with that, we have 13,000 observations detected in 6 years of operations on the moon. They're generally really small magnitudes, often more than an hour duration. They often have this really distinctive kind of shape. So they have this really, I don't know if everyone can see my mouse, but they have this kind of long rise time and then an even longer decay time. And that's really, really distinctive for all the types. We have no obvious distinct phases. This is the noise, this bit here. So picking the onset is really, really difficult. So picking the very first arrival is quite difficult. Often it's a very emergent signal. And then picking later phases, you know, it's really, can be really, really difficult. So yeah, so there's no, and often there's no obvious later phases. So we're pretty sure that there are later phases in there, you know, like phases coming off the core, for example. Being reflected in different ways from different boundaries within the moon, but they're obviously really, really hard to pick. And this isn't a particularly nice example, but it's not particularly bad either. So this is what we're dealing with. This is what lunar seismograms look like. And that tells us a couple of things kind of already about the moon, that we have to have a very, very highly scattering environment, that the energy has to be being bounced off all kinds of heterogeneity and fracture. And so there's clearly something going on about the shape of, about the structure of the moon, that it kind of tells us a lot about that already. And secondly, we also need low attenuation, because if we had this very highly scattering environment, which on Earth, you know, the whole thing would be over in a couple of, you know, just a few tens of seconds. So to have it last for a whole hour, you must have very, very low attenuation, and that seems kind of well borne out by the data. So then I come on to the second topic, which is moonquakes. So yes, there really are moonquakes on the moon. The one I showed already was a meteoroid impact, so they're obviously hitting the surface. They're not technically a moonquake, but they certainly give us a really nice signal. We also get this kind of moonquake called deep moonquakes, which seem to be roughly halfway to the center of the moon. And then we also, and these ones are kind of tidally driven. Then we get some shallow moonquakes, which tend to be a bit bigger and closer to the surface. And I'll show you some seismograms from those. We also know that we have this kind of very strongly scattering layer. This is what's causing the layering seems to be, the scattering seems to be much stronger at the surface. And so anything which comes below that scattering layer has a slightly different signature to the things anything which originates either within it or has to travel through it twice. So these are some examples of different types of moonquakes. We have the deep moonquakes, which are about 800, 900 kilometers depth. We have meteoroid impacts, we have shallow moonquakes, and then we also have artificial impacts, because the scientists were kind of clever enough to work out that if they fire the Saturn IV stages at the moon, when they're finished with them, then they're going to get a really amazing signal. So you can see that in terms of the scale is very different here to these ones. These ones are pretty small. So yeah, just to talk a bit more about these kinds of moonquakes, we start with deep moonquakes, which are the most numerous events. They tend to be very, very small. And they have this quite distinctive shape. So again, we have this kind of rise time, and then it falls off. But these are much, much steeper and have a much sharper onset, and then they kind of come off a bit quicker. We can't always see distinct P or S arrivals. And the really cool thing about these signals is that they can be stacked. And so even something which is absolutely tiny can be stacked, and then we think we can see other things, other boundaries or whatever from different parts of the moon. So we have, that brings us to having a theory of the deep moonquake nests. And the theory is that because these signals can be stacked over tens of minutes, that means that they must be coming on the same path. And if they're coming on such a similar path, then they have to come from these very tight little clusters within the moon that seem to be activated at different points in the tidal cycle. And they're estimated to be about 800 kilometers deep. Then we move on to meteoroids. They're usually small, not always. And sometimes the P wave is reasonably distinct. This one's got quite a nice sharp onset. So you get some kind of onset, and then you get this, again, the same shape with every type of moonquake. Then we get shallow moonquakes, where there really aren't very many of these. They're really cool because they're often quite a nice big signal. There are about 28 of them. They're sometimes larger magnitudes. The S energy is distinct, and the way it's plotted here, it's not that distinct. But if you can just about make out that there's this little bulge here before it suddenly increases. And the bit where it suddenly increases is the shear wave energy coming in. So you get this kind of little distinctive shape where it's kind of got almost like a nose cone in front of a plane out in front of it, and then it rises really quickly. And when we say shallow, we don't really know how deep they are. They're estimated between 30 to 100 kilometers depth, and they could be much shallower or probably much deeper. So they're not particularly well constrained. And finally, I go to the artificial impact. This impact is what happens when you fire one of these at the moon. They're brilliant in terms of their science. They're brilliant though, because we know exactly where they were, and we know all the other things about them, like the trajectory and how fast they were. So we can really use them to calibrate the rest of our models, and they're really brilliant for helping us do the velocity models, which I'm going to talk about later. And they look like large meteoroid impacts, and that's basically because they have a huge amount in common with large meteoroid impacts. So let's talk about the internal structure. So I've talked already quite a lot about this scattering, and this I think is a really nice diagram because it shows the kind of path that the energy has to take to be recorded at the seismometer. That some of them are coming quite directly. They're going sort of straight down beneath the scattering layer and then traveling through the mantle and then coming straight up. Some have this kind of bouncing trajectory where they're going all over the place, and these waves can keep going. As we know, they can keep going for about an hour. They're probably trapped in this layer while they're moving. So there, you get this kind of crazy path, and then you get, and then the whole thing together is that you get this this shape. This is an energy plot, so everything's positive, but you get again this slow rise time, and then even slower decay time, and that's it has to be part of that scatter and the lack of attenuation. So next I'm going to talk about the velocity models which we can get. And for people who aren't used to using velocity models, it's something which seismologists do a lot, where we can use how fast the seismic ray arrives to say, you know, how quickly each bit of the material it passed through was. And with many, many rays, then you can start to build up a picture of the different like the different layers and the gradient within the model. So this picture is obviously quite busy, but if, for example, this is the P wave velocity, VP, and so you can see that you start off pretty low, and then you increase quite quickly, and then you have a pretty constant velocity down to maybe around 1,200 kilometers depth. And then after that, things are very, very poorly constrained. So, but we do know several things about this. Kind of tells us a lot about the moon, that it's very low velocities near the surface. And then we have a strong gradient within the crust, which is this bit here. There's good agreement between all the different models within the mantle. It seems to be pretty well constrained. And then it's quite crazy after that. And so the models below that are pretty poorly constrained. And so we don't necessarily know what exactly how deep the crust is, how deep the core is, and then how and what the velocities are within there. And that's just a function of the ray paths, that the ray paths are rare that go that deep, and then if they do, then they're being scattered as well. So yeah, it's really not it's not ideal, rather than there's any kind of great problem with the way people are doing things. So yeah, that's this is what we can kind of tell about the moon, and we seem to have this kind of change just here, which tells us what we have, like where we're hitting the base of the crust. So let's think about some future missions and what we could learn. There's actually quite a few future missions being, like, none of them are actually in progress, but we are considering seismometers for various different missions at various different stages of proposal. So the first one is the Lunar Geophysical Network, which would have 4 different seismic and geophysical stations based around the moon. That's being proposed, will be proposed, I think, in 2021 or 2022. Then we're thinking of having a package which could be carried on Artemis, which would be a bit similar to the way that the other astronauts took the other packages, hopefully a bit simpler this time. We don't have to kind of fiddle quite so much. The European Lunar Geophysical Observatory is being proposed right now, and I'm also interested in something called Moonquakes, which is having a seismic network delivered by penetrators. So penetrators are kind of little-shaped objects that you use to embed the instrument beneath the ground. So they have a huge advantage. Obviously, one of the disadvantages is making your instrument and everything that supports it be able to be, not die when it hits the surface. So those are some possible future missions. I'm going to talk specifically about a particular seismometer called the Silicon Seismic Package. That's a picture of it. It's 25 millimeters across, and it has it's got many advantages. It's small, it's lightweight, it's just etched on a silicon wafer, so it's kind of very compact little device. It's deployed on Mars. It's kind of its predecessor, the SSP, is part of the seismic package. It's not the only seismic package, but yeah, it's part of it. So if we just talk about, so this is a plot, I'm afraid it's a bit busy, but this is a plot of how we think the microseismometer might work on the moon. We need to make some changes to make it work on the moon. So if I just talk you through some of the lines on this plot. So we have some events. There's a pretty big one, and then some smaller ones. So the green one is the smallest, like a really small event that we can just see. And then this range here is the noise of the Apollo instruments. So you can see that it is a range, and we're plotting the percentiles, the 9th, 30th, 50th, 70th, and 90th percentiles. You can see that there's a range there. This is on the short period instrument, which was used on the moon, and this is a medium period instrument used on the moon. So you can see that there's a big range, and very unsurprisingly, the lowest events that we can detect are within that noise. So sometimes the noise is a little bit higher than the smallest events that we can detect, and we don't really see events kind of right at the bottom of the noise, but that's pretty unshocking. So the kind of and sorry, this is the predicted line for the seismometer itself. Is where we think the changes that we have to make it work on the moon bring the noise floor down slightly below what it is on Mars, and so we end up with this curve here. So the takeaways from this is that we think that we're never going to detect events below the noise floor of the moon. That's just not very likely to happen. And we also think that Apollo was recording pretty close to the noise environment of the moon. It seems we don't seem to have quite got to the noise environment of the moon. We're not quite there. We don't get, we're still, you know, that sometimes we're actually recording the noise of the instrument rather than the moon. But anyway, we think this range suggests that we are recording, we're pretty close is the main argument. And that means that the seismometer above 0.3 hertz is predicted to be better than Apollo, which is great because it's a 25 millimeter seismometer, or a sensor at least, and so we can do quite a lot with it, including putting it on penetrators and various other cool things. So that's something which we're doing with that. So how many events do we think we can get? Well, there were a lot of events recorded with Apollo. But some of them are so tiny that you can barely see them at all. So this plot here is just the estimate of expected events above a signal to noise ratio of 2.5, which is not that great actually, and there's not a huge amount you'll be able to do with those. So we think we're getting around kind of 70 events per year per seismometer. So obviously the more seismometers you have, the better. And on top of that, if you can get them really close to each other, then you can start stacking the signals. So there's plenty of, we do think that we'd be seeing events, and there's lots to do with this kind of work. So the my last slide is to do with the key questions which were kind of raised by Apollo and raised by the work that we've done so far that haven't yet been answered. So one of the first ones is so what is the thickness of the core? And I showed you that the core is not particularly well constrained. So we think that we can do more with more seismometers. Is it liquid? We think it is, but does it have a solid inner core? Then we're really interested in how thick the crust is at each point, and how it varies across the surface of the moon. We want to know how deep are the deep moonquakes, and then we're interested in how they break and what their relationship is to the tide. Are they being forced by the earth tides? We want to know how deep that scattering layer is, because that tells us something about how the moon's been fractured over the course of its history. And we're interested in just measuring the number of meteoroids that hit the moon every year, because we have, that we'll be able to estimate that pretty well around a certain area around our seismometers. So generally the kind of questions that we can answer with seismology talk about the structure and the differentiation of the moon. And when you have a better picture of that, we can also think about its formation and evolution. And it's thought that the moon rose very early in its history, and therefore we're actually kind of looking back in time as well, that we can see something kind of coming back from much earlier in the solar system. So yeah, so that's what I've done. That's what we're interested in. There's a lot of people to thank, including the 500,000 people who worked on Apollo. More. But anyway, thank you for listening.